program, which myself and Professor Sharma has developed, is mainly looking at the integrated water management, water system design, and decentralized system. That's the area which we will be covering. And in that, we have initially we'll start with the history of integrated water management, decentralized system, different terms of decentralized and water system design approaches, because across the world they are being called with different names, but doing the same thing. And we'll talk about the history too. Then we'll talk about the frameworks, how we are looking for integrated water management approaches for a city area, how we should approach. We'll talk about it. We'll do some examples. The title may not be exactly the same, but we'll be talking about the same aspect. Then different type of water system design systems, and what are the functionalities of those systems. We will share about the different guidelines which are available for designing different systems, water system and design, and integrated water management. We'll talk about a lot on rainwater tanks. So in diesel rainwater tanks, which are on allotment. So three terms which I will be talking a lot is household scale, which is allotment or a lot, single house. Clusters, a group of houses, which can be multi-story or single-story houses. And the development scale means a new suburb, it can be houses of 1,000 homes. So these are the terms which we'll be talking about a lot in my presentation. Then we'll talk about the sustainable planning design for infill, because what is happening now that with the increase in population, either the density in the cities is changing because the high-rise developments are coming in the areas, either removing the existing houses or utilizing the land which is available, vacant land available for many, many years. So there is a lot of change in density in the area. And because of that, it is becoming difficult to supply water supply or wastewater systems services through the existing system. So either you need the upgradation of those systems, or either you need alternative means to provide those services. So these are some of the aspects which we'll be covering during, and then the climate change aspect, Professor Jain will be talking about, and Dr. Sharma will be talking about rainwater. So we will be covering different aspects of urban water systems during those 5 days. So this is a general introduction of what you're going to cover. So I will start my first lecture or presentation on the history of water system and design, integrated water management, and decentralized system. Just give us a minute, and I will go to my slides. So to start with, we will talk about what is integrated water management, water system and design, the history, and decentralized system. And why we need moving from conventional systems to integrated water management, because we are, this is a general outline what we're talking about, and then the last we'll have some discussion about these type of systems. So why we need these approaches, because our systems which are already there, the conventional systems, and which are centralized systems normally, facing different constraints or challenges. And one is the population growth, resulting to that is the urbanization, climate variability, as a lot of discussion going on nowadays about the climate change. There will be different pattern of rainfall over time. And there is a lot of work which is going on in predicting what will be the impact, what will be the expectation in future, and what will be the nature of rainfall, evaporation in future. So there is a lot of, and because of that, there will be shortage of impact will be on the existing water sources. And that will also have impact on the stormwater systems because of that uncertainty, because of the impact on the intensity of the rainfall. So we have to think about what impact that is going to have on our stormwater systems. Resource constraints, because of the changes in the rainfall pattern, we will have shortage of resources. That is, again, a challenge which we have to meet to provide water supply systems in future. And also, because there is an increase in wastewater and stormwater flows, the existing infrastructure is having a lot of impact because of that. So, and also the another limitation which you might be seeing, the regulatory agencies, they are putting increasing pressure in reducing the nutrients load into the natural environment. So there is a restriction being imposed by regulatory agency. I think over here we have an Environmental Protection Agency, Central Pollution Control Board or something. They are also putting significant pressure on. And to meet the system to provide services with these existing approaches like centralized systems, we have to upgrade our system significantly. And that will need a huge amount of resources and money and planning. So are we looking different approaches? We are looking different approaches for mitigating these impacts. So this is just an example of a centralized water system. The water is coming from a source, and then it is distributed. In this diagram, you can see just a river or a dam, but there can be a battery of tube wells, the groundwater sources, or maybe they're taking water from natural river, or there can be different sources. But what is happening is that we are treating that water and supplying to the urban areas, and from there, the stormwater and wastewater is collected or treated and then disposed to the receiving environment. But what is happening in the areas is that in all the corners are expanding, so the boundaries are expanding. And also within the cities, there is a change in the density. So the demand of water, the services are increasing further. And because of that, the existing system may not be sufficient for the sources, infrastructure capacity. So what can be done to some extent is that we can also think of providing, we can think of providing some approaches at the allotment scale by having either rainwater tank systems. We can also have grey water applications, and we can also provide some type of stormwater detention approaches at allotment scale. And these type of approaches can also be utilized in the existing environment and also in the new development area too. And the second type of approach is which can be utilized at larger scale, which can be cluster scale or development where the new development areas are coming up, where we can have localized wastewater treatment and reuse. We can have either communal rainwater tank systems, and we can also have water sustainable design to mitigate the impact of the increase in, to reduce the flow of stormwater. So there can be different approaches, and that means we are talking about a system which is a hybrid type of system. The centralized, one layer of centralized system, and we are putting another layer of decentralized systems. So these can be the future approaches which are being implemented in some part of the world to see how we can reduce the expenditure on the infrastructure by adopting alternative means of systems. So if we take the definition, there are a number of definitions which you can see on integrated water management, but this is one which is quite commonly used. The integrated urban water management is a comprehensive water management approach that demands consideration of the whole urban water system, from supply catchment to the receiving waters and all physical and non-physical influences of its performance. The system boundary, we are talking about integrated water management approaches that should be have from the source to the disposal point. In between, we have the whole infrastructure. So we are looking as a urban cycle as a whole, not looking only the urban areas, but from where the water is being received and where the water is being disposed, the impact on the receiving environment and impact on the environment from where we are taking the water. So this integrated water management should cover all the complete boundary of that receiving and all that environment. And also we are talking about the multiple stakeholders. So the integrated water management is also very closely considers the requirement of all these stakeholders. There is another definition which is also being widely used is the integrated water management promotes a coordinated planning approach to drinking water, wastewater, and stormwater services that takes into consideration the broader implications of sustainable development, including energy demand, greenhouse gas emissions, waste generation, nutrient losses, life cycle cost, and community acceptability. So the community should be the part of the overall integrated water management approaches implementation. What happens is that in many areas where there is a new development, there is no community, no one is living in those areas. So normally we take the information about the community acceptance from where already been communities living in new areas. So the information about liking, disliking of various systems, because what happens is with integrated water management approaches, there is a responsibility of the community too to manage some of the systems, which we will talk about in later. The second type of approaches which we are normally talking about a lot is water sustainable design. The definition which the Australian government developed is basically the integration of urban planning with the management, production, and consideration of urban water cycle. So the urban planning should include the protection and conservation of the urban water cycle. That ensures urban water management is sensitive to natural, hydrological, and ecological process. So the water sediment design, basically, that should integrate with the urban plan. That's the most important aspect of mitigating the impact of those challenges which we talked about. And mostly it is focused on stormwater management. And the idea is that how we can mitigate, how we can reduce the pollutant loads, which has increased because of the urbanization, and how we can reduce the overall the flow into the natural environment or the receiving environment. So the intention normally is that can we have a similar flow rate which was there when it was a greenfield area, and we can also have similar nutrient load before what was there before the development. So there are a number of guidelines being developed by different states, then how we can reduce those loads and what approaches are being applied. And normally it is the water sediment design approaches. We will talk about what are those technologies, approaches, and where, what type of technology will be more suitable. So decentralized systems is basically, these are the systems that can provide water, wastewater, stormwater services at the cluster, means the group of houses, at a development scale, and that utilize alternative water resources, including rainwater, wastewater, and stormwater based on fit for purpose. The term fit for purpose is the most important aspect, whether the water which is available, the source which is available, whether it is suitable for drinking or potable purposes or not. If, say for example, in many part of Australia, the rural part of Australia, and maybe over here in India too, the rainwater is one source for drinking purposes. The wastewater, which is locally treated, that can be utilized for irrigation purpose of parks and garden, and even the gardens which we have at house scale, allotment scale. So decentralized systems, they can be managed as a standalone system or integrated with centralized system. So means that can be the part of a hybrid system, centralized and decentralized system. The advantage in this type of system is that overall, wherever we are generating a resource or the resource is available, the network is very small. Whether it is a supply network, because if it is a communal rainwater tank system or individual rainwater tank system, we are treating the localized few houses water supply, wastewater, we are supplying back to the houses for fit for purpose. So fit for purpose for wastewater is normally either you supply due to toilet supply, flushing, or you garden watering. So these type of systems are becoming very common in many parts of the world. I think in India too, rainwater harvesting is becoming a lot popular because of those challenges which we talked about. And in our discussion, we will be having one complete lecture on rainwater harvesting, modeling, and all those aspects. So these are some of the type of decentralized systems which are for water supply, wastewater treatment, and stormwater harvesting and reuse. Overall, if you see the link between the integrated water management, water system and design, and decentralized system, integrated water management is the overall picture, where decentralized system and water system and design, they are sitting. So basically, everything is linked together in overall planning of integrated water management approaches. We all know about the resources, the water sources which are available, and they should be utilized. In decentralized system, basically, it is a localized water resource, rainwater and wastewater and grey water treatment and reuse is possible. And sometimes we use the combination of various resources. So basically how to have this planning for a new suburb, we will be sharing a software which will help in looking what resources can be utilized where, and then what impact that will be having on potable water supply, how much we can reduce sustainably the potable water supply, the fresh water sources. So basically, most important part which we have to keep in mind is the fit for purpose, and also another aspect which is very common or implemented and encouraged by the government or the water utilities is the demand management. How we can reduce the demand of water, up to what extent we can go. So for example, in Melbourne we have a target of 155. So one person should not utilize more than 155 liters of water per day. So earlier it was more than 250 or 260. So because of the water shortage over time, they try to encourage by different means how we can reduce the water demand. So water conservation and demand management is very important aspect of overall integrated water management. So normally when we see these approaches, we look for economics, we look the environmental aspect and the community. And when we are looking those three aspects when providing services, the technical aspect also becomes a very important component of that. We call it TBL, triple bottom line assessment, and we'll talk about a lot about this type of how we can approach and how we can assess different options and to look the suitability of those options based on this triple bottom line approach. So we talked about the total urban water cycle, and you can see that in the overall urban water cycle, the catchment, the urban area, and also looking the alternative water sources which are being generated, which can be generated at the urban, within the urban areas. And there is a lot of potential to utilize those resources. As you can see in this diagram over here, there is a decentralized system approaches which can also be implemented in looking the overall total urban water cycle context. So decentralized systems, water system urban design has a very good potential, important aspect of overall planning of water systems in future. The water system urban design approaches, I have taken this slide from from the guidelines which was developed by Adelaide State Water Organization. They have listed those 12 type of water system urban design approaches, and they have provided in detail the guidelines for all those 12 type of water system design systems. So I have provided the link. I think maybe tomorrow when we're talking about these systems again, I will go through the website and I will request all of you, if you can download those guidelines. They are for the design of systems. That will help a lot in future to look into how those systems are being designed. So in this slide, you can see these are the different approaches being used by under the integrated water management or water system and design approaches. Demand reduction, demand management is one. Rain garden, roof, green roofs, green walls, infiltration systems, rainwater tanks, pervious pavements, again management of the stormwater, urban water harvesting, reuse. Basically it is more important for stormwater harvesting. Cross pollutant traps, which are being provided to trap the coarse pollutants before the stormwater is discharged into the receiving environment. Then bioretention systems for streetscape, soils and buffers. These are some basically the ways, not providing the concrete channels, but these type of systems can reduce the pollutant loads significantly or it is discharged into the receiving environment. Wastewater management locally and the siphonic roof water systems. This is basically what's developed in Adelaide University locally, but it has also been included in the water system design approaches by the Greater Adelaide Research. So we'll talk about a little bit about these systems in our presentation. So drivers for water system design approaches. What are the benefit of providing those type of approaches or systems? Basically, since 1980, urban planning and development has increasingly taken into account the natural water and nutrient cycles, with water flow managed as would have occurred on the original greenfield site. Basically, what we are talking about is that when we have a new urban development, whatsoever the flows were coming at that time from that area, we will try to manage that the similar flow should be there once the development has been taken. That means the nutrient loads, that means the flow, the peak flows, should be managed at the same level. And to do that, we have to use or apply water system and urban design approaches to manage that. Basically, the idea is this way we can protect the ecology of our natural systems, because the water which is being discharged is being finally discharged to natural water systems. So basically, these type of approaches can manage the stormwater quality and quantity, which is very essential. Otherwise, the flora and fauna in those natural systems will have significant impact. Mitigating the risk of increasing flooding. Mitigating the risk of increasing flooding, especially when there has been some previous history of that in the greenfield environment. So basically, water system design can also be utilized for mitigating the flood from that area. Greening the urban, and the one is the harvesting of rainwater and stormwater for potable and non-potable application. The quality of rainwater is much better than the stormwater. So if you can collect the roof water directly, store it, partially treat it, disinfect it, and then it can be utilized as one source for drinking water supply, as a source for drinking water supply. And for the stormwater, we can treat it, we can use it for fit for purpose based for irrigation and toilet flushing. Greening the urban environment to reduce the heat island impact. That's another aspect which is being considered in urban areas. The temperature is increasing in urban areas. Yeah. Water system urban design can help in reducing that impact. And also that it can improve the aesthetics of the urban area, because it will help in well-being the community if you have more green areas where community can sit and enjoy. That will help in improving the well-being of the community. That's another aspect which is being considered in providing water system design process. So these are some of the drivers of implementing water system design. And there is a reference which is available, and we will share with you. I will show you some of the published material and books after this session, where you can see the references, and also you can get more information and knowledge from those references. So what is happening is progressive change in stormwater management because of this water sustainable design. The stormwater management has undergone progressive change since 1980, driven by an inevitable increase in impermeable surfaces, leading to an increase in stormwater runoff because of the urbanization, because of the decrease in the pervious areas. There is more impervious area. That's why the flow has increased. Basically, we are talking about two types of responses. One is the detention of stormwater, basically stopping, keeping it for some time, and then releasing it slowly. So that means we can decrease the peak flows in the stormwater network. That's one aspect. So we are not reducing the flow or reducing the quantity, but we are decreasing the, we are regulating the flow in this case. So basically, this can involve the construction of wetlands where we are holding for a short period and then releasing it. So we don't have to increase the capacity of the existing network system by it. The another approach is basically retention. In retention, either it is being infiltration process, the percolation, evaporation, and transpiration, and also the domestic use and industrial use. So these are some of the approaches where we can retain part of that stormwater. So these are the two, all those water system urban design approaches either will be using those two approaches, either it's retention or retention. So basically, these are the two aspects which you have to consider a lot. These developments resulted in a variety of technological descriptors such as low impact development. So water system urban design we are talking about, in across the world, they are being used the same retention and detention approaches, but they have different name in different part of the world. Somewhere they call it low impact development, LID. In some areas they are green infrastructure. And in some areas, in some countries, sustainable urban drainage systems, water system design, low impact urban design and development, and water sensitive cities. So these terms are being utilized in different part of the world. I will go through some of the history of those terms, but overall, their functionality is the same. But they started, these approaches started in different part of that different time. They're engineers, professionals, they put different names to those terms, but ultimately it is detention and retention aspect. More information can be seen on this chapter, which we will be sharing in a book. But you can download that information. So if you're looking at the history of water system design, initially it was more supplying water. So it became the water supply cities. We start with. Then there was issues with the public health many years ago. Then the sewer systems developed. You might have heard in the history there was cholera and other because of the urban human waste, because of the rainfall. So many diseases developed because it was not properly disposed of away from the urban areas. Then the sewer system developed that time. The next development was for the drainage city, removing the stormwater away from the urban areas. After that, we tried to look into the waterways, protecting the receiving environment. Then the overall, the urban water cycle of the city, starting from catchment to the disposal. And the drivers were fit for purpose sources conservation, promoting water-based production. And then now we are here somewhere, water self-urban cities, basically where the drivers are adaptation, multifunctional infrastructure, and urban design, reinforcing water self-urban behaviors. So this is how, over time, the history of water self-urban design development took place. Now we are somewhere in some part of the world, and we are somewhere in some part of the world. So this is slowly progressing. So now we'll talk about a little bit about these terms, where in what, which country, which part of the world these terms are being used. So in the United States of America, they call it low impact development or green infrastructure. And initially it was reported in somewhere in 1977, covering land use planning in Vermont. And then EPA, US EPA developed some guidelines for Clean Water Act, for the Clean Water Act. And LID focused on stormwater quality and peak discharges, basically the same aspect. So there is not much of a difference what water system is going and this low impact development. Their focus was the same. But the drivers were different in different parts of the world. We'll talk about a little bit more on those. So basically, LID focused on stormwater quality, peak discharges, complemented with the concept of green infrastructure, which links landscape architecture and urban ecosystem with water cycle management. So the green infrastructure, incorporation of green roofs, green walls, rainwater tanks, swales, permeable pavements, improved infiltration, wetlands, green spaces. Basically, this is all about those approaches we talked about in the water system and so on. So this was initiated somewhere in 1997 in the US with the name of low impact development and green infrastructure. In Canada, it is low impact development again, and because they're neighboring countries, so they picked up the same name. But over here, it was initiated somewhere in 1970. First developed the detention basins on ditch and pipe systems. So basically, how they want to reduce the flow in the pipe network for in the stormwater, in the case of stormwater. In 1992, province of British Columbia generated a stormwater planning guideline that recognized detention ponds and which can mitigate flooding. So that way they started, and now they have developed guidelines for the design, water system design. The 13 LID structures are listed in those planning guidelines. And there is a reference provided which will help you if you are interested to look a little bit more information about the LID in Canada. In the United States, United Kingdom, UK, they call it Sustainable Urban Drainage System. And the concept of Sustainable Urban Drainage System was developed in UK, published guidelines documented in year 2000 for Scotland and Northern Ireland, and separately for England and Wales. So they started developing guidelines, how to design those systems, how to provide those systems, but they called them sustainable urban design systems. And the goal was to try to mimic the natural hydrology that is usually adversely impacted by urban environment. So looking from the urban development which is coming up, how we can have a similar flow and the stormwater quality which was before before providing any development there. So that was the main goal in adopting these type of systems and approaches. In Germany, they call it decentralized urban design, DUD. It was figured in Germany and also began adopting water systems, SUDS and water sustainable design. I think there is a reference available in 2009. They also have developed guidelines. Basically, they also focused on water and stormwater flows which are heavily polluted. Basically, the idea was to reduce the pollutant load by using those approaches. So water system design is mainly focused on stormwater management, quality and quantity both, if you see in almost all part, but stormwater harvesting is becoming another aspect of management. In France, they are also using techniques, alternatives, PA. These are retention and infiltration, adopting green roofs, gardens and lagoons to encourage stormwater infiltration and reuse. Basically, again, the same. And in 2014, International Office of Water in Lagos established a demonstration portfolio of alternative techniques. So they also started using, but the reference is available in 2014. Basically, again, similar approaches being used across in France too. But I think you can see in US and UK, they're more permanently used and developed much more before the other parties started taking. In Spain, they also have similar type of sustainable urban design drainage systems, and they also start developing the guidelines for designing those systems. Basically, again, the same type of retention systems with the aim to manage stormwater. In Australia, the term was developed sometimes in 1992 for application of water system design, and the Australian government Joint Steering Committee in 2019 developed guidelines for providing those services. So these guidelines are publicly available in the system. So these guidelines integrate the components of urban water cycle, water supply, wastewater, stormwater, and groundwater management with the urban design and environmental protection. Basically, it is again the question, the bigger picture is the environmental protection. In the guidelines which are being provided in Australia, that specifically indicates that when you have a development, there should be 80% reduction in total suspended solids, 45% reduction in total phosphorus, 45% reduction in total nitrogen, and 90% reduction in gross pollutants. So basically, whenever you are asked, any developer is going for any developing a new area, they have to show through the guidelines, adopting these guidelines, showing that how they're going to reduce the total pollutant loads which are being generated because of the new urban development. And the most important aspect you can see over here, the post-development peak 1 year average era should be same as after the development. So that is very, very important aspect, that pre-development and post-development 1 year RI flow should be the same, as close as possible. And that's why they have to adopt different approaches based on the size of that development. Which approach will be more suitable? New Zealand is also having similar approaches, and they started sometimes in 1991. They call it low impact urban design and development, but name is different, but approaches are almost the same. And they also have developed their guidelines, which is available through the New Zealand standard NZ 4404. China is quite active recently in management of stormwater. They call it sponge city. And basically, they want their cities to absorb all the stormwater which is being generated. And this is a concept which is being utilized quite. The shortage of water resources and pollution of the water environment has become a constraining factor in the sustainable development of China. So their president in 2013, they talked about sponge cities where stormwater can be naturally conserved, infiltrated, and purified for potential reuse. So that is a driver initiative coming from the top. And their target is also there that under the guidelines, cities in China are to be collected and utilize 70% of the stormwater, with 20% of urban areas meeting the target by 2020. And the proportion will increase into 80% by 2030. So there is a lot of pressure on cities to adopt sponge cities, to manage the stormwater. Because the driver is, again, if you see the shortage of water resources and pollution of urban environment because of the urbanization, okay, the increase in the flows. In developing countries, some part it is starting adopting water system design approaches. They call it low impact development, water system and design. Some part it is being adopted. But the difficult part is that difficult for urban developments and redevelopments to address the sustainability of water, where a significant portion of the population still doesn't have access to basic water and sanitation. That is a limiting factor. So before we start thinking of water system and design, low impact development, and before that we have to provide basic services, and that is a challenge. And in some part of India, we are also facing similar challenges too. So these approaches are good, but you need some significant amount of resources to provide those services. In Japan also, they are also starting using water system and design approaches. So in conclusion, what we can say is community principles increasingly being recognized within different terms. Basically, they're the same. But the drivers can be different. In Europe, focus on seawater overflow protection and flood management. Together with the access of green space. In USA, they focus on water quality protection, green space aesthetics, and flood mitigation. In Australia, they focus on water-based ecosystem protection, littoral zone conservation, and coastal park. Because most of the cities in Australia, they are along the coastal. So whatsoever we are discharging, it is the receiving environment is the seas, basically. In China, we focus on stormwater harvesting and environmental protection because of the shortage of resources and the impact on the environment. WSUD LID principle seeks to mimic the natural hydrology of a site by using decentralized management measures. Basically, these are the decentralized approaches. Okay. Still, we have some time. So maybe we can have some discussion about the implementation of these approaches in India. And you can also share some your experiences and those who are working in different, working in industry or conducting research, what difficulties they face or they think, what changes are required. The initiative by the government is very important part, but community too have some contribution towards. What we have seen in Australia is that the state started encouraging community householders to have rainwater tanks. And those who were more inclined towards protecting environment, they start putting their own money in installing rainwater tanks. But on the other hand, the state also provided some subsidies in installing rainwater tank system. And at some point, because of the for 10 years there was a drought and there was very limited water available in the dams for water supply. So during that period, state enforced new homes to have rainwater tank systems. But with the social research, what we saw that those who were more environmentally active, they could manage their rainwater tanks properly. And where it was enforced by the government, some of the rainwater tanks started were not functionally, they're not functioning good or well after a certain period of time because those residents were not managing those systems properly. So there can be those challenges where the community can contribute towards the water planning in one way. So the message is that we should think of that this is a resource which is in very much, one is in demand and also the resource is very limited. So how best we can utilize and manage those resources is a very challenging part. And we all should try to contribute towards that management to some extent. Any comment, any suggestion? How best we can utilize those approaches, can provide services in India? Yes, please.
So, although it's very complicated issue, there are several aspects and there are so many approaches, and it varies from case to case. Like in some parts, particularly metro cities like Delhi, Mumbai, I think the major issue is how we can timely, clean these stormwater drainage systems. They do already have systems, stormwater drainage channels are there, but normally MCDs before the rainy season they try to, but most of the time they're clogged with lot of garbage and other things. People consider these as because they're open both the ends. Might be covered in some areas, sometimes they're not properly maintained. So maintenance aspect of the stormwater drainage channels is one important issue. And also the repair and timely cleaning of the clogging. That is an important issue. If they are properly, maintained and cleaned, then I think to a large extent the stormwater drainage system will not lead to the flooding. This is one issue. And another issue which which just came to my mind by listening to a presentation on integrated water management. integrated water management, it's fine, sounds and natural hydrology and the geohydrological units, that's idea is okay. But when there are different stakeholders, particularly the different states are involved, like the area where I worked in Madhya Pradesh, the two state governments. And not even state governments in the two, even in the Delhi, two different MCDs, the same government. So it's an issue of administrative control and the economic administrative aspects also come into picture. So how one can coordinate between these agencies, that is also a significant issue. So if we can devise a mechanism whereby the economic contribution, like polluter pays a price, or by penalizing, by constraints, and by also incentives. So the combination of these approaches, I think, would lead to some kind of success. That's my comment.
No, absolutely right. And these issues are not only in this part of the world, but these issues are also there in other part of the world where different stakeholders, agencies, they're not talking to each other. And they try to govern the way they like. It is sometimes the personality clashes, sometimes the political issues, sometimes the funding issues, who is going to contribute how much. But someone has to take the lead. And who is going to take that lead is a very big question mark. Maintenance is really a big issue. Even the community should play some role in it, because the open channels, the communities start putting it, considering it as a dumping ground. So that's why I said that we all have to contribute to some extent, where possible. Where our responsibilities, with those responsibilities, we can also contribute, just being a citizen of not only the country, the local area. If you consider the local area as our own backyard or the home, then I think we can also contribute to some extent in managing those systems. I think the management or operation is a bigger, major contribution, major issue, which we all are facing. The economic is another aspect, but operation and management is another very big. When I was working in UP Jallingham at Ghaziabad, I was managing a sewer system in Rajan Nagar area, and it was not handed over to the local municipality at that time, and GDA was managing it. We saw that every alternate day, one of the main holes from the sewer system was picked up, taken away, and there was even one child that died because of that. He was cycling and then he dropped into that. So who is responsible for that? Is it only the management who was responsible for managing those systems, or we as a human being? We all are responsible. We have to take share, how best we can manage, contribute. So these are some of the challenges which we were facing. So what we started doing is that whenever we're replacing a manhole, manhole cover, we were asking all the nearby residents, house owners, to actually sign on the paper that it has been replaced. That was one part of our responsibility, but this is not end of everything. So these are some of the challenges which we all face, I think, and that's why I think we all should see that where we can contribute in managing our systems. Okay? So this is one lecture which we can finish it now. I'm not sure how much time we have, Professor. 1 o'clock? So it's still 45 minutes remaining. Okay. Maybe we can pick up some more information. I can go through that where you can download. I can go through some of the documentation where the guidelines for water system design approaches developed by Adelaide, South Australian Agency. I can go through one by one. and you can download when you have time, because that will help you in looking in different type of systems, how they're designed, and the planning aspect, where they are more suitable. So I will go through to that site, and then I will show you some of that aspect.
Even with regard to these guidelines,
Sorry?
even with regard to these guidelines, I think that in a country like India, it's not possible to have a uniform guidelines. Because this is to some extent dependent on the topography as well as the geology of the place.
Absolutely right.
Because in places where we have very high water table, there are areas, for example, some states in India, you say, the river is very shallow, deep, relatively compared to the Gangetic plain where you have very thick and medium rivers. So there is a limit to what you can push into the soil. And even if you push into the soil, see, for example, you take some of the states in peninsular India, the river is very shallow. And if you push in too much water, in fact, if you have I read about the floods in 2018, 2019, etc. Too much of saturation, supersaturation of soil, in fact, has led to almost this soil behaving like a fluid, and that has actually triggered landslides as well. So, although it looks very appealing to say that rainwater harvesting, rainwater harvesting, of course, is a technology. It has to be adopted in places where you have real shortage of water and where you can store, but then that doesn't work everywhere in water and water to return. And from an operational perspective also, even in the cities where they are claiming that water does not, the drains are filled up, I would say that more than the drains we use as a dump yard, it is the improper construction of the drains which is leading to this problem. Because there are, I can cite specific examples where during a flood, the road is flooded, but the drain is completely dry.
Dry. So that means not designed.
Because in our system, construction of drain is given least preference, least importance. It is considered to be a very mean job. So at the local body level, this job is entrusted to a contractor, and without proper supervision, the drain is constructed. That way, in a peaceful manner, a block is constructed, and another block is constructed in some other year. And when you try to connect them, the inverse levels don't match, and ensure water does not flow. Because there is no proper supervision. In fact, drain construction is the most important thing. So, more than, it's not that drains are not there, but not being constructed properly, the grades not properly maintained, invert levels not properly maintained, set, because there is no supervision at all in this construction.
And
in this high water table areas, I can tell you, even the septic tanks which we are constructing, you find that because of this high water, see, sometimes the uplift pressure which is exerted on the tank, it causes this thing to
come up.
Come up.
So these are more technical and planning aspect of implementing, whether it is a drainage system. So still those approaches are good, but the question is the implementation is not proper. And in some cases where the water table is already high, quite high, then some of those techniques which we are talking about cannot be implemented or applied. Big impact on.
But then precipitation patterns are definitely changing, and that's how the type of precipitation is also changing, because now we have very intense precipitation of short duration.
Yeah.
Total rainfall in the year is almost the same.
Yeah.
But then
intensity for a short period is. Yeah.
See, normally this northeast monsoon ends by let's say middle of November or so, but this year even in December it is raining.
Yeah.
So when you have, and that too reasonably good rain. And similarly, the same thing in summer, April, May, there is rain. So already water does not, soil does not get desaturated to that level that it can take up that much water. That's
Yeah.
also an issue.
Because the rainfall is over a short period, but intensity is quite high. Earlier, it was more spread over the year. So these challenges everyone is facing, every part of the world. The climate change is not only one reason; it is across, and that's why we have started thinking. Okay, we have an existing stormwater network, and most of the stormwater mains street level, they are designed either for 1 in 10 years or 1 in 20 years. But now the intensity has changed because of the climate change. There will be overflow because the carrying capacity for that peak discharge is not there. And there can be inundation for some time over the road. So those challenges are being faced.
People in research claim that stationarity is not accounted. That's because of this stationarity is accounted. Intensities would have been higher, etc. But I think it is much beyond all this.
It is much beyond overall from those factors. When we start talking about the construction aspect, we will start talking about whether it should be now 1 in 30 or 50 years design. And mostly the main trunk sewers or trunk stormwater network, they are designed for 1 in 100 years. But the street level, it is designed for 1 in 10 or 120 years. And also when we start thinking about putting soils, which is a natural systems, they don't have much carrying capacity. The flow is not that fast in those. But we are talking about those systems because they can remove some of the pollutant loads. And also they have a functionality of percolation, infiltration, all those aspects. But with the climate change, I think those systems will also have issues in future. There is no one solution for every area. There is no one solution for every circumstances. I think over time we have to start change our thinkings and designing process and all those things. But overall, the designing construction, some of the practical issues like you talked about, that when we are starting piecemeal construction without looking the overall comprehensive design, one inward may not be channel, may not be meeting where you can take the flow further. These are the practical aspects, and how to mitigate or control over those aspects is there is some human factor too in those all aspects. And that's why I am more of view that as a human being, as an individual, we have some contribution somewhere in managing and designing those systems and for their ongoing upkeep. But yes, all those factors are very important. You also mentioned few, and you also mentioned few. And working in this area for so many years, these are the practical aspects which we have to face, and how we can find solutions for them. For these aspects is quite challenging.
Exactly what you are mentioning as gross pollutants, what is it?
Cross pollutants is basically traps where, like for example, it can be larger particles, it can be water bottles, all those can be trapped before it at first step, and they are regularly removed from there. For that, there are different type of infrastructure which are being provided. I think some of the figures we will be showing. So we will continue the discussion. It is never ending discussion. Being engineers, we all face those type of challenges. And I think when we start working in different organizations, different institutions, you will be facing different type of challenges, what we face at our time and what you will be facing in the future. We'll continue the discussion, very interesting. And that's why the communication has to be from both sides. So I talked about some of the design guidelines for different types of management design approaches. You all can go when you have time to that website, you can download. And I think this reference is already available in one of my slides. Over there, they're talking about starting from demand management to the rainwater tanks, rain gardens, roof infiltration system. Basically, they are quite a large, quite a comprehensive documentation which was done by South Australian government to provide. There are so many other guidelines too. We will have one session on guidelines on water sustainable design, but I found this one quite comprehensive. And it talks about each and every design approach, sorry, the water sustainable design approaches. You can download all those documents. It is freely available and very comprehensive written. So I will go through a little bit more. And they are talking about the design, mainly on the design and planning both. And you will see quite in detail that information which is available. We're talking about the pervious pavements, rain gardens, roof, green roofs, green walls. So there are other, and wetlands. So there are 14 or 15 chapters which are available under those guidelines, talking about each and every system, their design, planning, and also some of the examples are also given. So there is a one software which can be easily downloaded free from US EPA website, US EPA, Environmental Protection Agency, which is a SWIM model, SWMM, Stormwater Management Model. Okay, so I think we're talking about briefly about that model too. Using that model, we can have different options of water assessment design, and we can see the impact of those type of systems. How many systems you provide at the allotment scale, the cluster scale, development scale, and how much there can be reduction in the peak flows in the network, this drainage network, because of that. What will be reduction in the pollutant loads? So this software is easily, you can download free. and this is a very well developed software. Most of the commercial software which are available in the market, they're charging $5,000 to $10,000, and this is free. They are using the same engine. They're using the same engine, which is free. But what they have done is they have changed the front end and maybe some of the outputs which are getting maybe slightly better. And they are charging huge amount of money because of that. But this is very well developed software. I will suggest those who are working in stormwater area, they should start learning this software. There is a manual available, very well written, documented, and you can download everything from there. And all those type of WSCD approaches we talked about, you can see the impact of those by providing different sizes. So maybe during those 4 or 5 days which you are with us, during the time, try to download this and see the initial aspect of it. Very well developed, and it will provide you it is being used by researchers too in looking the impact of those type of systems. And you can see whether in some of the guidelines where we are required to have the same flow as the pre-development level, it can give you some idea how much and with what magnitude these systems should be provided, what system will be more suitable. So you can see the different scenarios and you can compare different scenarios, and then you can do the costing outside. I don't think it does life cycle costing, which you can be done outside using Excel sheets, and then you can compare different options, which will be best option for providing water assessment design in area to achieve certain objectives, whether it is the reduction in the nutrients or the pollutants, or it is the reduction in the flows. So you download this software, which is very good, and it is freely available from US EPA website. The office is in Cincinnati. They have their water group there, and they worked for many, many years to upgrade the software. So I will suggest to you to download and start using. And there are examples available in that manual, which they have provided how to use that software. And you can start with this simple application, and it is very widely used nowadays.
So how do we calibrate and validate certain parameters?
Okay, so basically, say for example, for any development area, we want to implement water assessment design. So we know the network. We will provide that network into the software. There are different ways of putting that network. And then what we need is basically the rainfall say for example, for last 2 years. How much is the flow being generated at the end point of that network? So we need that information, the data, for calibration and validation.
But land use will vary from.
So what land use will vary.
That's why you need different parameters.
So we start from the existing development. Okay. Say for example, in Roorkee, we know that for certain catchment, the flow is being discharged or receiving environment is such and such. So we have to measure the flow in the stormwater network. That's what I did in one of the catchment in Melbourne. That was 5.5 kilometer area, residential area. And we want to calibrate the similar type of stormwater software, which is another software, but using the same engine.
Fieldwork is
Fieldwork is required, yeah. Otherwise, how you can calibrate and validate, okay? But in some areas, based on their past experiences, they can provide some of the parameter values, which you can take from the existing literature
Empirical.
or use empirical. But say, for example, if you want to see the impact of those type of approaches today, but you can't calibrate and validate your software anyhow, you need some past data to do that. And data collection is especially putting automated systems for looking the flow meters and recording on a continuous basis and analyzing it is a very time consuming process. So until unless you have already the data available, only then you can calibrate and validate. But what you can do is that, okay, based on the assumption and the information which is available from the existing studies nearby, you can run these models, and then you put water sustainment design approaches, and you can compare to some extent. To some extent, it won't be 100% accurate, but it can provide you some good guidance that what type of system will be suitable. Okay. Yes, absolutely. Without having the past data, it is not possible to calibrate and validate these systems, which is very, very important aspect of looking the impact of any type of system on flows and magnitude of pollutants. So these are some of the, we'll go through one by one in maybe in next lectures. But what I will suggest to you that look and go through, download all those documents which are available, and start exploring and looking, and then we can have some discussion on. Otherwise, it is not possible to cover all the guidelines because they are very, very, very detailed information, but very useful. Okay. So maybe we can open one and we can have some discussion about. Although we'll be talking about rainwater tanks a lot in one of our sessions, but if you see this, there are a number of models available which are specifically here for designing, basically identifying the capacity of rainwater tank systems. And as you know that the capacity or the size of the rainwater tank system, that depends upon number of factors. One, what is the roof area connected to that? Number two is the rainfall pattern. Where there is quite a uniform rainfall, then more water is available for application because the use of rainwater from the tank is quite regular. Say, for example, in some cases, with the basic treatment, having UV, or depending on the quality of from where the rainwater, the type of roof, because different type of roof they have, they can have different pollutants even in rainwater. So the rainwater quality is not that 100% suitable just by directly using it. You need some basic treatment for it. And otherwise, you have to use it for other purposes, like for toilet flushing, garden watering. So roof area is one very important factor. Then what is the regular demand for it? Okay. Then different sizes, we normally try to identify the volumetric reliability of rainwater tanks. The volumetric reliability term is being used that what is basically the demand from the rainwater over a month or day or a year, and then what is the how much is the amount available from that rainwater tank. So if the rainfall is not very regular, then the water which is being available from the rainwater tanks will be quite small, and that means the reliability of the system will be very, very small. So we will talk about the software where you can provide all that data, and then you can see which size of the rainwater tank will be suitable for a particular application on a particular house, depending on the roof area, how many occupants are there, those who are utilizing that water. So we'll discuss about those type of software where you can design the capacity of the rainwater tank for allotment scale or a communal or a group of houses. So in this one, basically, the other aspect which you have to discuss about is that the water quality. And the water quality, that means the suitability of that water which is available for fit for purposes. Then in some cases there can be installation of some of the basic treatment processes like UV or some filtration process at a smaller scale, and then you can increase the application of the water at local scale. And then sizing is another important. And then we are also looking over time, what is the cost of the water? Because either you have a pumping system in a rainwater tank or it is by gravity. If it is by gravity, then the pressure in the system will be very limited. And some of the appliances may not be able to operate because of the low pressure. But as we have floating walls in our systems, it is much easier to have certain head or pressure in the system to fill those tanks. So there are a number of issues which we can discuss about the rainwater tank harvesting using the rainwater tank system. So please go through them, and we may be having opportunities to discuss about different type of approaches which are being discussed in this documentation. But this is not only one guideline, there are a number of other guidelines, but this one I found is much more descriptive and can provide significant amount of information. Okay. I think we can finish it for this session and meet for the next session. What time you are coming back? 2:30? Yeah. Okay. Let's have a more discussion about in this class.